Hello everyone and welcome to another lecture on machine learning foundations. In the last class we introduced and defined partial derivatives and gradients, and that is the first and standard interpretation of a gradient, which is it is a package containing the components, all the components of the partial derivatives. You have the partial derivative with respect to all the variables and put them all together into one vector, that is the gradient. That is the computational interpretation of the gradient. In today's lecture we will take a look at the other interpretations of the gradient, which are more geometric and more intuitive in nature than the computational approach. The first of which is the linear approximation interpretation. We have already seen linear approximations for one dimensional functions. If you have a function f from R to R and you want to approximate this function f around x close to x star, this is what you would do, right. F of x is approximately equal to f of x star plus f dash of x star into x minus x star. This is what we have been doing for linear approximations, and we denoted this term as the linear approximation of f around x star evaluated at x, and this is a valid approximation when x is close to x star. Right. This is for one dimensional functions. How can we do the same thing for functions from Rd to R? Right. In other words, its xn, now imagine V is a vector, a d-dimensional vector, and x is in its neighborhood. X is a d-dimensional vector and x is in the close to V. Right. Now you want to be able to approximate x. Right. The answer, I will give the answer first and then give various interpretations of it, which is f of x is approximately equal to f of V plus grad f of V transpose x minus V. You can see the similarities to the one dimensional case, right. So, f of x, you first have the f of V here, which corresponds to f of x star here, and you have grad f of V transpose x minus V, which corresponds to f dash of x star into x minus x star. We will break this down even further as f of V plus sum over I equal to 1 to d dou f by dou xi into xi minus Vi. I have just broken down the gradient into its components. Right. So, dou f by dou xi evaluated at the point V multiplied by xi minus Vi, and we will denote this also in a very similar way. We will call this as the linear approximation of f around the point V evaluated at x. And when is this approximation valid? This approximation is valid around x, approximately around x equal to V. Right. When x is close to V, this is a valid approximation of f. Okay. So, we will give one interpretation or one possible interpretation of this linear approximation. Okay. The way we do that is by breaking down into multiple one dimensional functions. We will make life easier for ourselves and just consider a function two dimensional function. This easily extends to multi-dimensional functions as well, but we will do that for just two dimensional function. Let us say f from R2 to R. F of x1 comma v2, f of x1 comma v2 is approximately equal to f of v1 comma v2. We are viewing the second variable as a constant, the first variable as the variable, right. So, we are approximating around v1. So, f of x1 comma v2 is approximately equal to f of v1 comma v2 plus dou f by dou x1 evaluated at v into x1 minus v1. Here is a small notation issue. We will, instead of calling it x1, we will call it y1. Right. this is just a standard one dimensional linear approximation, that is we are approximating the function f as viewing as just as a function of its first argument, that is f of y1 comma v2 is approximately equal to f of v1 comma v2, and we are using the partial derivative of f with respect to the first argument at v times y1 minus v1. Right. We will simplify, we will change the notation a little bit more, f of y1 comma v2 minus f of v1 comma v2 is approximately equal to dou f by dou x1 at v into y1 minus v1. Right. So, you can do the same thing for the second argument also, that is f of v1 comma y2 minus f of v1 comma v2, this is approximately equal to dou f by dou x2, which is the second argument at v into y2 minus v2. So, let us interpret these two approximations. What this says is, as I move from v1 comma v2 to y1 comma v2, that is as I move along the first axis, v1 changes to y1, v2 changes remains the same. This is the change in the value of the function. The value of the function changes by dou f by dou x1 evaluated at v into y1 minus v1. Similarly, here this expression says that as I move from v1 comma v2 to v1 comma y2, the change is given by dou f by dou x2 evaluated at v into y2 minus v2. But what we are now interested in is, what if both of them move simultaneously? What can I say about f of y1 comma y2 minus f of v1 comma v2? Right. The simplest answer is to, well, if one variable changes, this is the change. If another variable changes, this is the change. If both variables change, the change is simply given by the addition of these two changes, which is dou f by dou x1 at v into y1 minus v1 plus dou f by dou x2 at v into y2 minus v2. Right. Or in other words, now we will write down the full linear approximation, which is f of y1 comma y2 is approximately equal to f of v1 comma v2 plus dou f by dou x1 evaluated at v times y1 minus v1 plus dou f by dou x2 evaluated at v times y2 minus v2. Here we are going to make our life easier, and I am just going to call it the gradient of f at v transpose y minus v. This is exactly our linear approximation expression. Remember, that is the gradient of f of x is approximately f of v plus grad f of v transpose x minus v. Right. Or in other words, f of y is approximately equal to f of v plus grad f of v transpose y minus v. Y and x are just dummy variables, they do not really matter. Right. Okay. So, here are a couple of examples to run. Right. So, we will take a simple example first. Let us consider the function f from R2 to R, which is f of x1 comma x2 is equal to x1 squared plus x2 squared. Okay. Now, here is the question, approximate f around, I want a linear approximation of f around the point, let us say 6 comma 2. So, v is equal to 6 comma 2 in our case. What is f of v first? F of v is equal to 6 squared plus 2 squared, which is 40. Right. What is grad f of v? Grad f of v is 2v1 2v2, which is 12 comma 4. I mean, this is because grad f of x is 2x1 2x2. So, grad f evaluated at v in this case will be 2v1 2v2, which is 12 comma 4. With these we can actually give the answer, which is f of x is approximately equal to 40 plus grad f of v, which is transpose 12 comma 4 times x minus v, which is x1 minus 6 x2 minus 2. We can simplify this further and say 40 plus 12 into x1 minus 6 plus 4 into x2 minus 2, which would be 40 plus 12x1 plus 4x2 minus 72 minus 8, which would be 12x1 plus 4x2 minus 40. This is the linear approximation of f, which is x1 squared plus x2 squared around the point 6 comma 2. So, this is particularly valid around what point? Well, x1 comma x2 is approximately 6 comma 2. When your vector x is in neighborhood of 6 comma 2, this is a valid approximation. Let us visualize this further. Here is a contour plot of the function f, which is f of x is equal to x1 squared plus x2 squared. Here is the point 6 comma 2, and on the right you have the contour plot of the function LV of f, which we just derived here, just 12x1 plus 4x2 minus 40. And because this is a linear function, you can see that the contours are all straight lines and they are equally spaced. This is a linear function. A couple of things to note immediately, which is f of x evaluated at 6 comma 2, the value is equal to 40. You can see that this circle has value 40, and you can see that the linear approximation of f at the point 6 comma 2 also has the exact value 40. So, the linear approximation is exactly equal to the function value at the point of approximation. At the other points you do not know, but it is exactly equal at the point of approximation. And there are other properties also, but that is the first property that you should keep in mind. And the linear approximation does change with the point that you choose. If you want to approximate the function f around the point 6 comma 2, this is the linear approximation. But if you want to approximate the same function around a point, let us say minus 6 comma 2, the linear approximation changes. You still have that property, that is at the point you have 40 here and 40 here. Right. The f of v is exactly equal to LV of f evaluated at v. Right. At a general point x, this is not true. Right. At a general point x, you only have approximation f of x. The moment you change v to x, this is not exactly equal, this is only approximately equal, and that is also true only when x is approximately equal to v. Right. Only when around x equal to v do we have this expression. So, that is the linear approximation viewpoint, and the linear approximation is completely defined by the gradient. Right. And the same way that we have a linear approximation viewpoint for one dimensional functions and tangent line viewpoint, we can have a very similar viewpoint here, which is you can use tangent planes as graphs. Right. This is the tangent plane interpretation of the gradient. That is, if you have the graph of the linear approximation of f around the point v, that is the graph of LV of f, which is going to be a plane. Right. Recall, graph of a function f from Rd to R is a subset of Rd plus 1. Here you have a 3-dimensional plot of the function f of x is equal to x1 squared plus x2 squared. So, the graph of LV of f is a plane, because LV of f is a linear function, and linear functions, the graph of linear functions correspond to planes. The graph of LV of f is a plane that is tangent to the graph of f. At the point v comma f of v. So, v is a d-dimensional vector and f of v is a scalar. So, this is together is a d plus 1 dimensional vector. So, for example, here you have the blue curve corresponds to the blue surface corresponds to the graph of f, and the orange plane corresponds to the graph of the linear approximation of f around the point V. You can see that this graph of the linear approximation is a plane which is given and it touches the surface, the blue surface at a point, and that point is exactly equal to V comma f of V. So, this is the other interpretation, that is we have the linear approximation interpretation of gradient, then we have the tangent plane interpretation. The tangent plane is also given by the linear approximation, which in turn is given by the gradient. Okay. And we have the next interpretation which uses the contour sets directly. Right. Here is the statement for the gradient, which is you can say that the gradient of f evaluated at, let us say at some point V is going to be perpendicular to the contour set given by, or the level set given by the set of x in Rd, such that f of x is equal to f of V. For example, let us say you take the point minus 6 comma 2 and the gradient of f at that point is simply minus 12 comma 4. So, what I have done here is I have taken the point minus 6 comma 2 and I have plotted the vector minus 12 comma 4 as a vector here. The lengths do not matter, only the direction matters. You can see that the direction, this black arrow is almost perpendicular, it is in fact exactly perpendicular to this level set. What is this level set? This level set is exactly equal to the set of all x in Rd such that f of x equal to f of V, which is f of x equal to 40, right. This is the level set corresponding f of x equal to f of V, which is f of x equal to 40. And you have the gradient of the function f at V is minus 12 comma 4, which is perpendicular at that point. And I am not going to prove this completely, but what I am actually going to prove is this statement, which is quite obvious, which is that the gradient of f at V is actually perpendicular to the set x in Rd such that the linear approximation of f evaluated at x is equal to f of V. So, these two statements are not the same, but not same as of now, but we will they are actually the same under certain extra regularity assumptions. But this statement however is very easy to prove. Why is that? Because this on the set on the right side is actually a plane, right. Why is that? You have linear approximation of f at x is a linear function of x, and this exactly planes have a perpendicular vector inbuilt to them. What is that? Well, we will evaluate this set. This set is simply the set of x in Rd such that f of V plus grad f of V transpose x minus V is equal to f of V. Right. We will do some term moving around, we get this is a set of x in Rd such that grad f of V transpose x is equal to grad f of V transpose V. And this for the equation of a plane is set of x in Rd such that W transpose x is equal to B. If you have such a plane, you would already know that the vector W is perpendicular to that plane, and you can see that this is exactly of that form. Grad f of V corresponds to W. So, grad f of V is actually perpendicular to this plane, which we have proved now. Okay. So, that is the other interpretation of a gradient, that is the gradient of a function at a point V is going to be perpendicular to the contour passing through that point. Okay. Yeah. Next we move to another useful application or interpretation of the gradient, which has to do with directional derivative. What is a directional derivative? We have already seen an example of directional derivative, which is, well, we will first say an English redefinition of the directional derivative. We will define directional derivative of the function f at the point V along the direction u. So, you have the function f from Rd to R, u and v are vectors in d-dimensional space, u and v are elements in Rd, So, this is the notation for, I am going to read this as the directional derivative of the function f. I will write this directional derivative of the function f at the point v along the direction u. This is how you read this statement. What is the definition of this? Well, the definition is going to be, first create some space here. This is limit alpha approaching 0 f of v plus alpha u minus f of v by alpha. Let us try to interpret this expression. What this saying is, we want to move from v to along the direction u. You are at the point v and you want to move along the direction u, and you are trying to quantify the rate of change of the function as you move along the direction u. That is the directional derivative of f along u. Okay. How will we compute this? Right? Here you can use our linear approximations, because alpha is going to approach 0, you can approximate f of v plus alpha u using linear approximations. This is going to be limit alpha approaches 0, f of v plus alpha u is approximately equal to f of v plus grad f of v transpose alpha u minus f of v by alpha. You can see that f of v cancels and alpha also cancels. So, you are left with grad f of v transpose u. So, this is nice and particularly interesting, because it says that to compute the directional derivative of the function along any direction, all that you need to do is to take the dot product of the direction with the gradient. And this is in particular, this is nice because you are let us say in machine learning in practice, you often want to minimize a function, which means that you are most approaches take an iterative thing where you are at a current iterate, let us say v, and you want to decide which direction to move, right. You are going to move to a new iterate from v to let us say v dash, but you want to decide which direction to move. A very natural notion is you are at you can choose to move at the direction which decreases the function the most or increases the function the most if you want to maximize it. So, the notion that you are looking for is to what direction to move, so that you can increase or decrease the function the most, and the directional derivative is a very important tool for doing that. We will actually attack that next, and before we do that, however, we will take a slight detour to to actually give a very basic inequality known as the Cauchy-Schwarz inequality, which is useful for controlling the inner product of two vectors, grad f of v transpose u. Right. What is that? Well, you have, let us say you have two vectors a and b, right, who they are d-dimensional vectors, their components are a1, a2 dot 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 ad, right, and similarly b1, b2 dot 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 bd. You have two d-dimensional vectors a and b, and you want to be able to control their inner product, you want to be able to control a transpose b. What we can show is a transpose b is upper bounded and lower bounded by these two terms, which is upper bounded by norm a times norm b and lower bounded by minus norm a into norm b. This norm is a standard Euclidean norm that we have already defined, which is norm a is simply square root of a1 squared plus a2 squared plus dot 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 ad squared. So, A transpose B is upper bounded and lower bounded between these two terms, and you also happen to know that when does this equality happen. You want to know when this equality happens, and there is a very clear characterization for that. This equality happens when A is equal to alpha times B, where alpha is a scalar which is negative. If you have a negative scalar alpha and A is equal to alpha times B, then you have A transpose B is exactly equal to minus norm A norm B. And when does this equality happen? Well, this equality also happens when A is equal to alpha B, but alpha is a positive scalar. So, in other words, if you want to maximize the term A transpose B, you will choose B is equal to A is equal to alpha B and alpha to be greater than 0. And this will all lead us to the next question here, which is, let me delete this. Now you want to find the direction of steepest ascent. Let us say now you are trying to maximize a function f. Let us say you have a function f and you want to maximize it. You are at the point current iterate is v, right, and you want to choose a direction. Find a direction u that maximizes the directional derivative. You want to get maximizes the rate of change of f as you move from v along u. Or in other words, you want to maximize the directional du of f evaluated at v. Find u which maximizes this term. That is your goal, and we will do it a little bit more formally now. What is a direction? A direction cannot have arbitrary length, right. So, we will fix the direction to be have a unit norm, right. So, find u in Rd such that norm u is equal to 1 and which maximizes the directional derivative of f evaluated at v. But we already know this is exactly equal to grad f of v transpose u. So, v is fixed, the current point is fixed, the only thing that is not fixed is the direction along which you move. So, you want to find a u which maximizes grad f of v transpose u, and that is already given by the Cauchy-Schwarz inequality, which means that you should pick u to be a scalar multiple, a positive scalar multiple of grad f of v. Right. And we already know that u is a unit norm vector. So, alpha is simply going to be 1 by norm of grad f of v. So, this gives the other interpretation of the gradient, which is the gradient is simply the direction of the steepest ascent. Right. If you are at a point v and you want to move along the direction which increases the function the fastest, you would choose the gradient. Right. So, that is the other final, that is the other interpretation, which is the direction of steepest ascent. We can finally wrap this up by saying you are at a point, let us say v, you have a function f from Rd to R, you are at a point v in Rd. Now let us say you want to minimize this function. What all directions can you go? What are the valid directions such that f decreases? Right. Or in other words, for what values of u can you say the directional derivative of f along u evaluated at v is less than 0, or in other words this is grad f of v transpose u less than 0. So, the set of descent directions is simply the set of u in Rd such that grad f of v transpose u is less than 0. So, this is another tool that you will need when you do optimization, that is the set of directions along which you can move so that the function value decreases from the current value. So, that is your descent direction. These are all descent directions. With that we will wrap up the alternate grid interpretations, and there are some simple, there are some slightly advanced rules which I will briefly skim over. We will not go into great detail along these because we will not be using most of these, but we will do that anyway. The same way that you did for functions f from R to R, you had linear approximations and you also had higher order quadratic approximations. You can do a very similar thing for functions f from Rd to R also as follows. If you have a function f from Rd to R, the linear approximation f of the is simply given by f of x is approximately f of v plus grad f of v transpose x minus v. This is valid around x is equal to v. This was the linear approximation. You can do a higher order approximation the same way that you did for one dimensional functions. However, it is a little bit more complicated, which is, you can also say f of x is approximately equal to f of v plus the first term looks the same, grad f of v transpose x minus v. The second term on the other hand is half x minus v transpose, well, the Hessian of f evaluated at v into x minus v. I will not go into great detail into expanding the second term, but it is analogous to the quadratic term that we had for one dimensional functions. That is, you have f of x, this is exactly equal to the linear approximation, and the extra term you have this grad squared f of v, which is called the Hessian. This term is a d cross d matrix called the Hessian, and x minus v is a 1 cross d vector, x minus v transpose 1 cross d vector, and x minus v is a d cross 1 vector. Together this is a scalar. I will not go into great detail on this, but you might find more advanced optimization algorithms use a quadratic approximation than a linear approximation, but most of machine learning you will be sticking to linear approximations, which is this. And the same way that you had maxima, minima and saddle points for one dimensional functions based on the derivative, you have a very similar situation here with gradients and maxima, minima, saddle points. That is, if f of x is minimized at some point at, let us say, some point v, then you have that grad f of v is the 0 vector. But it is not true the other way around. Grad f of v equal to 0 does not mean that f of x is minimized at v. But however, if your function is minimized at v, then grad f of v equal to 0, but it is also true for maximi. So, any point where grad f of v equal to 0, the set of v such that grad f of v equal to 0 is called critical points. These points are called critical points. Note however that gradient is a vector, right. So, this 0 here corresponds to the vector 0, not a scalar 0. For special classes of functions, critical points can be shown to be exactly equal to minima, but in general critical points are not minima, not guaranteed to be minima or maxima. But in either case, critical points are interesting points to analyze. If you want to find the maxima or a minima of a function, you can just restrict your attention to points which satisfy this condition. This is called the first order necessary condition for optimality, and you only focus your attention on critical points and check whether they can be candidate minima or maxima. This is another application of the gradient where you set the gradient to 0 and find interesting points which are critical points and check whether they satisfy your condition. Right. With this we will wrap up